So this video is for those of you who are studying for the final exam of the first semester of college physics. So let's start with this problem. By the way, for each of these problems, make sure to try it first, pause the video, and work on it. Once you have the answer, you can play the video to see if it matches up with what's on the video. So let's go ahead and begin. A container has a mass of 50 grams when empty. When filled with water, the combined mass is 220 grams. When a container is filled with another fluid, the combined mass is 185 grams. What is the density of this fluid? The density of the fluid is going to be the mass of the fluid divided by the volume of the fluid. So we have this empty container, which has a mass of 50 grams. Now, when we fill the container with water, the mass is going to change. It's going to be 220 grams. So what is the mass of water in this container? The mass of water is going to be the difference between these two masses. So it's 220 minus 50. So it's 170 grams. Now, because we know the mass of water, we can calculate the volume of this empty container. But how can we do that? Density is mass over volume. If you multiply both sides by V, the density times the volume is equal to the mass. So to calculate the volume of water, we need to divide by the density, represented by the symbol rho. So the volume of water is going to be the mass of water divided by the density of water. The mass of water is 170 grams in this example. The density of water is 1,000 kilograms per cubic meter, but we're not going to use this value. The density of water is also 1 gram per milliliter. We're going to use that value. So the unit grams will cancel, giving us the volume in milliliters, which is just going to be 170. Now the volume of water is going to be the same as the volume of the empty bottle, because the fluid takes the shape of its container. So now that we have the volume of the empty bottle, in order to calculate the density of the fluid, we need the mass of the fluid. So let's draw a picture with the bottle and the other fluid. Let's use a different color. Let's say this fluid is red. So the combined mass of the container and this fluid is 185 grams. So the mass of the fluid is going to be the difference between the mass of the fluid and the bottle with that of the mass of the empty bottle. So it's 185 minus 50, which is 135. So now that we have the mass of the fluid and the volume of the empty bottle, we can calculate the density of the fluid. It's going to be the mass, using this formula, 135 grams divided by the volume of 170 milliliters. .135 divided by 170 is 0.794 grams per milliliter. So this is the density of the fluid in these units. What is the density of the fluid in the units kilograms per cubic meter? What would you say? Let's talk about how to convert it. So let's start with what we're given, 0.794 grams per milliliter. Now we need to convert grams to kilograms. You need to know that 1 kilogram has a mass of 1,000 grams. So the unit grams cancel. Now let's convert milliliters into liters. 1 milliliter, or rather 1 liter, has a volume of 1,000 milliliters. Now what is the conversion between liters and cubic meters? Both are units of volume. You need to know that 1,000 liters is 1 cubic meter. And you can also cancel these numbers. 1,000 divided by 1,000 is just 1. So it's simply 0.794 times 1,000, which is 794 kilograms per cubic meter. In physics, the density of certain materials is reported in units of kilograms per cubic meter, but in chemistry, the units for density is typically grams per milliliter. So just keep that in mind. To convert from grams per milliliter to kilograms per cubic meter, just multiply by 1,000 and you'll get the answer. To go the other way, divide by 1,000. Number 2, calculate the force exerted by the atmosphere on a 5-meter square surface at sea level. The air pressure at sea level is 1.013 times 10 to the 5 newtons per square meter. So let's say this is the 5 by 5 square meter surface, and there's air above it. Air has mass. The weight of the air exerts a force on this surface. We know what the pressure is, but what is the total force exerted on this particular surface? How can we calculate it? Pressure is basically force divided by area. So if you multiply both sides by A, we can see that the force exerted by the atmosphere over a surface is the pressure of the atmosphere times the area. So we have the pressure, it's 1.013 times 10 to the 5 newtons per square meter. And then area is basically length times width. So 5 meters times 5 meters, that's going to be 25 square meters. So we can see that the unit square meters will cancel, giving us the unit of force, which is in newtons. So 1.013 times 10 to the 5 times 25, that's going to be 2,532,500 newtons. So we can say that's approximately 2.5 times 10 to the 6 newtons. So that is the force that the atmosphere exerts over this entire surface at sea level. Number 3, calculate the pressure at a depth of 15 meters below the surface of the ocean. The density of seawater is 1,025 kilograms per cubic meter. So go ahead and try this problem. So let's begin by drawing a picture. So let's say this is the ocean. Now, let's say this is the ground surface, and we want to find a pressure at this point. We also have the weight of the air above the ocean. So the pressure at this point is dependent on the weight of the ocean above it and also the weight of the air above it. So the pressure is going to be the pressure of the atmosphere that is exerted above that point and the pressure of the ocean or the water that is above that point. Now we have the atmospheric pressure. We know it's 1.013 times 10 to the 5 newtons per square meter. What about the pressure exerted by the water above that point? This is basically the gauge pressure, which is the pressure above the atmospheric pressure, and it's equal to the density of the fluid times the gravitational acceleration of the Earth times the height of the water above that point, in this case the depth. Now this number is equal to 10 to the 5 is basically 100,000. So this is 101,300. Now the units newtons per square meter is equal to pascals. So we can write PA for pascals. The density of water is 1,000 kilograms per cubic meter. The gravitational acceleration of the Earth, 9.8 meters per second squared, and the depth is 15 meters. So this is going to be 1,000 times 9.8 times 15 So that's 147,000 pascals. That's the gauge pressure. The absolute pressure, which is P, that's the total pressure. That's going to be the sum of those two numbers, which is 248,300 pascals. So that is the absolute pressure at this point. You know what? I made a mistake, and I used the density of water instead of the density of seawater. So let me just correct that mistake. So this should be 1025. So that's going to affect our answer slightly. 1025 times 9.8 times 15, that's going to be 150,675 pascals. So that's what the gauge pressure should be. So the absolute pressure is 251,975 pascals. So this is the final answer. That is the pressure at this point. Number 4. A 1,500 kilogram car rests on a circular hydraulic lift with a radius of 3 meters. What is the minimum force that should be applied to the other section of the circular hydraulic lift, which has a radius of 0.1 meters? Part B. How far down must the left section of the hydraulic lift be pushed in order to raise the car to a height of 5 centimeters? I forgot the word A here, but it should be there. So what's going to happen is we're going to apply a force, F1, and we're going to push the left section down. That force will exert a pressure on that part of the hydraulic lift, and that pressure will be evenly distributed throughout this fluid, and it will exert an upward force that will lift the car, if this is strong enough. Now, the pressure exerted at the left section, let's call it P1. The pressure exerted on the right section, we'll call it P2. These two pressures are equal. So we have P1 is equal to P2. Pressure is force over area. So P1 is F1 over A1, P2 is F2 over A2. Our goal in part A is to calculate F1. The area of this circular portion of the hydraulic lift, the area of a circle is pi r squared. So this is going to be pi times r1 squared. F2 is going to be the weight of the car. The weight of the car is mg. A2 is the area of the right section. That's pi r2 squared. If we multiply both sides by pi, we can cancel it there. So our goal is to calculate F1. Let's multiply both sides by r1 squared. So F1 is going to be the mass of the car, which is 1,500 kilograms, times g, times r1 squared. R1 is 0.1 meters. R2 is 3 meters. So let's go ahead and do the math. So it's 1,500 times 9.8 times 0.1 squared divided by 3 squared. So the force that we're going to apply at the input is 16.3 newtons, or 16.3 repeated. So this is the answer for part A. Now let's talk about this. But first, let's get rid of some stuff. The hydraulic lift is basically a force multiplication device. It took our force of 16.3 newtons and multiplied it to a point where it's able to lift the car. The weight of the car is 1,500 times 9.8. That means F2 has to be at least 14,000 700 newtons to lift the car. So we've multiplied the force by 3 squared over 0.1 squared, which is 900. We multiplied the force by a factor of 900. So the hydraulic lift can take a small force, multiply it, and create a large force to lift up heavy objects. But there's a cost. Nothing comes free. The work that we do at the input must equal the work that we do at the output, because energy must be conserved. And so this is going to lead us to part B. How far down must the left section of the hydraulic lift be pushed in order to raise the car to a height of 5 centimeters? In order to apply a small force here, we need to push it down for a very long distance. And if we're going to get a large force here, this is going to go up by a very small distance. Work is force times displacement. So the input work, we'll call it W1. The output work is W2. So W1 is going to be F1 times D1. W2 is F2 times D2. Solving for D1, we need to divide both sides by F1. So it's F2 times D2 over D1. Over F1. So F2 is this value here. That's 14,700 newtons. F1 is this number, 16.3 repeated newtons. And we're going to multiply that by D2, which is 5 centimeters. To convert centimeters to meters, divide by 100. So D2 is 0.05 meters. So D1 is going to be 45 meters, which is a lot bigger than 0.05 meters. So in order to multiply this small force into a large force, we need to push down the left section very far in order to get a large force where it's only going to go up by a small amount. So there's a trade-off here, as you can see. Energy must be conserved. So that's basically it for the hydraulic lift. You can use it to multiply forces. Number 5. A 450-gram block of wood with a density of 820 kilograms per cubic meter is placed in water, and we have the density of water. Calculate the upward buoyant force acting on this block of wood. So let's draw a picture. So let's say we have some water, and there's like this block of wood in the water. Now, here is a question for you. Will the wood sink or float? Is it going to go down to the bottom or up to the surface? To answer that question, we need to compare the densities of the two objects. In this case, wood and the fluid water. Because wood has a lower density than water, it's going to float. The reason why it floats is because there's an upward buoyant force acting on this object. Now, according to Archimedes' principle, the buoyant force on an object immersed in a fluid is basically equal to the weight of the fluid displaced by the object. So the buoyant force is equal to the weight of the displaced fluid. Now, the weight of anything, we know it's mass times gravity. So in this case, the mass of the fluid times g. But how do we calculate the mass of the fluid displaced? We know that density is mass over volume. Multiplying both sides by v, we can see that mass is density times the volume. So we can replace m with the density of the fluid times the volume displaced. So thus we have the equation for buoyant force. It's the density of the fluid times the gravitational acceleration times the volume of the fluid displaced, which is equal to the volume of the object. So this is the formula that we need to use to get the answer. So let's plug in what we know. The density of the fluid is 1,000 kilograms per cubic meter. The gravitational acceleration is 9.8 meters per second squared. Now we need to calculate the volume of the block of wood. We said that density is mass over volume. How do we calculate volume? Well, let's put this over 1 and cross multiply. So here we have 1 times m, which is m, and that's equal to P times V. Dividing both sides by P, or rather rho, that's the symbol for density. It's the Greek letter, or the Greek symbol rho. We see that the volume is going to be mass over density. So the mass of the block of wood, that's in grams, so we need to convert that to kilograms. So we have 450 grams of wood, and you need to know that 1 kilogram is equal to 1,000 grams. So whenever you convert and set it up in such a way that the unit that you don't want gets canceled. So 450 divided by 1,000 is 0.45. So the mass is 0.45 kilograms. The density is 820 kilograms per cubic meter. Now the unit kilograms will cancel, and so we're going to get the volume in cubic meters. 0.45 divided by 820, it's a very small number. It's 0.0005488 approximately cubic meters. So now let's talk about the units in the final part of our equation. Notice that the unit cubic meters cancel. So what we have left over is kilograms times meters per second squared. So what unit is equal to kilograms times meters per second squared? If you recall, Newton's second law says that F is equal to ma. Kilograms is the unit of mass. Meters per second squared is the unit of acceleration. And the unit of force is newtons. So 1 Newton is a kilogram times 1 meter per second squared. And so we're going to get the force in newtons. So it's going to be 1,000 times 9.8 times 0.0005488. So that's approximately 5.38 newtons. So this is the upward buoyant force acting on this block of wood. Number 6. A 9.54 gram rock has an apparent mass of 7.28 grams when submerged in water. What is the density of the rock? Now there's a formula that we could use when dealing with apparent mass problems. The density of the fluid is equal to the density of the object, in this case the rock, times 1 minus the apparent mass divided by the mass of the object. Here's the rearranged formula of this equation. The apparent mass is equal to the mass times 1 minus the density of the fluid divided by the density of the object. Now, for those of you who want to know how you can derive these formulas, I'm going to post some links in the description section of this video, and you can check it out. Or you can do a YouTube search, type in apparent weight organic chemistry tutor, and this video should come up where it explains how to derive these formulas. So the one we're going to use for this example is this one here. Let's rearrange for the density of the rock or the object. So we need to divide both sides by this portion of the equation. So the density of the rock is going to be the density of the fluid divided by 1 minus the apparent mass over the mass. The fluid is water. So that's going to be 1,000 kilograms per cubic meter. The apparent mass is 7.28 grams. The actual mass of the rock is 9.54 grams. Go ahead and plug this in. You may need to put this in parentheses on the bottom. So you should get 4,221 kilograms per cubic meter for the density of the rock. So that's it for this problem. Number 7, a block of wood floats on water. What fraction of the block of wood rests above the surface of the water? So let's say here we have a block of wood. And it's floating over water. So this is the portion that is below the surface of water. But we want to find a portion that is above the surface of water. How can we do that? We could use this formula. The volume of, in this case, the block of wood that is submerged divided by the entire volume of the block of wood. This is going to be equal to the density of the block of wood divided by the density of the fluid. So right here, this whole thing, Vs over V0, that will give us the fraction of the block of wood that is below the surface of water. So that's going to be the density of the object, which is 850, the object being the wood, and the density of water, which is 1,000. 850 divided by 1,000 is 0.85. So this tells us that 85% of the block of wood is below the surface of water, which means that 100 minus 85, or 15%, is above the surface of water. So this is the answer. So when dealing with a question like this, you just need to know the density of the object and the density of the fluid. And so dividing those two will tell you how much of the block of wood or the object is submerged in water. And then the fraction that remains is the part that's above the surface of the water. Number 8. Water flows through the left section of a pipe at 8 meters per second with a pressure of 230,000 pascals. The cross-sectional area of the left and right sides are 0.20 square meters and 0.10 square meters respectively. The right side is 5 meters higher than the left side. Part A. What is the speed of the fluid at the right side of the pipe? Well, let's draw a picture first. So here's the left side, and the right side is going to be 5 meters higher. So water is flowing on the left side at a speed of 8 meters per second. The area of the left side is 0.20 square meters. The area at the right side is 0.10 square meters. What is the velocity at the right side? Well, we need to be familiar with something called a volume flow rate. The volume flow rate at the left side and the right side are the same. The rate at which water flows on the left side and the right side, that's not going to change, given that the fluid is an incompressible fluid. If the fluid is incompressible, the density of the fluid will remain constant. Q, the volume flow rate, is the rate at which the volume changes with respect to time. Volume is basically area times distance, if you think of a rectangular prism, divided by time. Distance over time is speed. So the volume flow rate is equal to the area times the speed of the fluid. So Q1 is going to be A1 V1, Q2 is A2 V2. So with this formula, we can now calculate the speed of the fluid at the right side of the pipe. So A1, that's 0.20 square meters. V1 is 8 meters per second. A2 is 0.10 square meters. And let's calculate V2. So let's divide both sides by 0.10. 0.20 divided by 0.10 is 2. And 2 times 8 will give us V2, which is 16. So let's think about what's happening here. The right side has a smaller cross-sectional area than the left side. As a result, the speed increases. So when you decrease the cross-sectional area of a pipe, the rate at which the fluid flows through the pipe increases. To think about this like in a real-life scenario, imagine if you have a water hose, and imagine releasing the pressure where the water is coming out of the water hose. Now, let's say if you take your thumb and block a portion of the hole at which water comes out. The rate at which water is going to come out is going to be a lot faster when you block a portion of the hole with your thumb. It's going to be shooting out at a higher speed. And so we could see the truthfulness of this principle here. As you decrease the cross-sectional area, water is going to come out at a faster rate, such that the volume flow rate on the left side and on the right side remains the same. So the answer for part A is 16 meters per second. So now let's move on to part B. Which side has a higher pressure? Would you say the left side, or would you say the right side? What would you say? Now, something that you need to be familiar with is that as the speed of the fluid increases, the pressure decreases. Pressure is going to be higher on the side with the lower fluid velocity. Now, the second thing is the height. As the height increases, the pressure also decreases. And you could figure this out based on Bernoulli's equation. But these are some things that you want to keep in mind. So, on the left side, the fluid is moving at a slower pace. And on the right side, it's moving at a faster pace. Now, the height on the left side is at a low position, and the height on the right side is at a high position. So we expect that the pressure on the left side should be higher than the pressure on the right side. Now let's prove this with Bernoulli's equation. Let's move on to part C. Calculate the pressure of the fluid on the right side of the pipe. On the left side, it's 230,000 pascals. So on the right side, it should be less than 230,000 pascals. So let's go ahead and calculate P2. And V2 we said was 16 meters per second. So here's Bernoulli's equation. P1 plus 1/2 rho V1 squared plus rho G H1. That's going to equal P2 plus 1/2 rho 2 V2 squared plus rho 2 GH2. So P1 is 230,000 pascals. Rho 1, that's going to be the density. The density of water, we're dealing with water in this example, is 1,000. V1 is 8. Now, the right side is going to be 5 meters higher than the left side. So if the left side is our reference level, it's going to have a height of 0. Now looking for P2. Rho 2 is still 1,000. V2 is 16. G is 9.8. And H2, that is 5 meters higher than the left side, so it's just going to be 5. Now let's do the math one step at a time. So here we have half of 1,000, which is 500, times 8 squared. That's going to be 32,000. And then 500 times 16 squared. That's 128,000. And then 1,000 times 9.8 times 5 is 49,000. So to calculate P2, it's going to be the sum of the stuff on the left side minus the stuff on the right side. So it's 230,000 plus 32,000 minus 128,000 minus 49,000. So P2 is going to be 85,000 pascals. As we can see, it's much less than the pressure on the right side. Now let's talk about this. So the left side has a higher pressure than the right side. Now you could think of pressure as force because force is basically pressure over area. So anytime there's a pressure, there's a force exerted. The velocity on the left side is lower than the velocity on the right side. So on the left side, there's a stronger force than the force on the right side because the pressure on the left side is higher. And so we have a net force that accelerates the fluid towards the right. So thus we can see why the speed increases from a slow speed or a low speed to a higher or a faster speed, since there's a net force accelerating the fluid towards the right. And also because the force on the left is higher, it can push up the fluid to a higher position. And so this helps us to see why the pressure is higher on the left side. It needs to be in order to lift up the fluid to a higher position and at the same time accelerate the fluid to a higher speed. All of that takes energy. And you could think of pressure as being a form of stored potential energy when it relates to fluids. Number 9. What is the speed at which water will flow out of the tank shown below? The water level is 20 meters higher than the point at which water is going to flow out of the tank. How can we calculate the speed at which water will flow out of this tank? Well, let's talk about how to derive the formula that is associated with Torricelli's theorem. We could use energy. The water that's stored in this tank, which is at 20 meters higher than the level where it's going to leave, it has potential energy. Anything that is above a certain reference level in terms of height has potential energy. And when the water begins to move, it's going to have kinetic energy. Anything that has motion has kinetic energy. So in this example, potential energy is being converted to kinetic energy. We can set them equal to each other because energy must be conserved. Potential energy is mgh. Kinetic energy is 1/2 mv squared. So we could cancel the mass. If we multiply both sides by 2, this is going to be 2gh is equal to v squared. Then if we take the square root of both sides, we'll see that the speed at which water is going to flow out of the tank is the square root of 2gh. Now, we could use pressure as well to get a similar equation. The change in pressure due to height is going to be the same as the change in pressure due to speed, because as the height is decreasing, the speed of the water is going to increase as it flows out of the tank. The change in pressure due to height is density times gravity times height. The change in pressure due to speed is 1/2 density times the square of the speed. And we could find these two portions in Bernoulli's equation. So the density of the fluid will remain the same. Now we need to multiply both sides by 2. 1/2 times 2 is 1. So we get 2gh is equal to v squared, and taking the square root of both sides, we'll get this formula as well. So you can get the same equation using energy or pressure. So now let's calculate the speed. It's going to be 2 times the gravitational acceleration of 9.8 meters per second squared times the height, which is 20 meters. So if you plug this in, you should get the square root of 392, and that's equal to approximately 19.8 meters per second. So that is the approximate speed of water that's going to flow out of this tank, based on Torricelli's theorem. Number 10. What is the net force that a wind moving at 80 meters per second can exert on a flat roof with an area of 300 square meters? And we're given the density of air, it's 1.29 kilograms per cubic meter. So let's draw a picture, just to understand what's happening. So let's say this is someone's house. Let's say this is the window. Now let's say there's wind traveling above the house. What happens to the pressure if the velocity is increasing? Inside the house, you have still air. So the air is basically not moving inside the house. But outside the house, there's a wind. Now, based on Bernoulli's equation, when the velocity of the fluid increases, the pressure should decrease. So above the roof of the house, there's going to be an area of low pressure. Inside the house, you have an area of high pressure. And so pressure is related to force, thus there's going to be an upward net force that will lift up the roof of the house if the wind is strong enough. So in a hurricane, where you can have speeds up to 150 miles per hour, that could be strong enough to basically pull off the roof from a house, depending on how strong the roof is and how the house is constructed. But there's an upward net force that can lift up the roof. Our goal in this problem is to calculate that net force. Now we know that pressure is force divided by area. So force is going to be pressure times area. The changes in pressure that is due to a moving fluid or a fluid with speed is 1/2 rho v squared. So this is the formula we need to calculate the force exerted by this or caused by this wind. The density of air is 1.29 kilograms per cubic meter. The speed at which the wind is moving is 80 meters per second. Don't forget to square it. And the area upon which the pressure will be acting on is 300 square meters. So it's going to be 0.5 times 1.29 times 80 squared times 300. So the force is going to be 1,238,400 newtons. So that is the force that will be acting on this roof with a given area. So notice that the area is proportional to the force, or rather the force is proportional to the area. As the area of the surface increases, the force increases. And as the wind velocity increases, the force increases. Here's a question for you. If you were to double the area, by what extent will the force increase? Notice that this is a to the first power. If you double the area, the force will double. If you triple the area, the force will triple. But now what about the wind speed? Notice that F is proportional to the square of the wind speed. So if you double the speed, 2 squared is 4, the force will quadruple. If you triple the speed, 3 squared is 9, the force will increase by a factor of 9. And so the force increases greatly with wind velocity. Number 11. A 300 Newton force is used to compress a spring by a distance of 0.35 meters from its natural length. The spring is attached to a 0.25 kilogram block, which rests across a horizontal frictionless surface. Calculate the spring constant. So let's begin with a picture. So let's say this is the spring, and this is the block attached to the spring. And right now, let's say it hasn't been compressed. So it's in its equilibrium position, which means x is 0. Now, we're going to apply a force of 300 newtons to compress the spring. So let's say it's now at this position. So it's 0.35 meters from its natural F, which means it's 0.35 meters to the left of where it was here. So we could say that x is negative 0.35 at this point, since it's to the left of the origin, so to speak. Now we have the mass of the block. And so the mass of the block is 0.25 kilograms. With this information, how can we calculate the spring constant? The spring constant is represented by the symbol K. Now, based on Hooke's law for springs, F is equal to negative Kx. So K is going to be negative F divided by X. So the force is 300 newtons, and X is negative 0.35. You could ignore the negative sign. K has to be positive. So you should get 857.14 newtons per meter for the value of the spring constant. So this is the answer for part A. Now let's move on to part B. How much potential energy is stored in the spring? The formula that we need is this equation. The potential energy of a spring is 1/2 kx squared. So K is 857.14. And in this example, X is 0.35. Now we could put negative 0.35 if we want to, but once we square it, the result will be positive. So the potential energy stored in this spring is approximately 52.5 joules. So that's it for part B. Now, part C. How fast will the block move when it's released from the spring? So once this force is removed, this block will want to go back this way. How can we calculate the speed at which it's going to move to the right? Now, what we need to do is set the potential energy equal to the kinetic energy. So right now, when the spring is compressed, it has stored potential energy. But once you release the block from the spring by removing this force, the block is going to move to the right. All of the stored potential energy in the spring will be converted to kinetic energy, or energy of motion, in the block. So we have the potential energy, which is 52.5. The kinetic energy is 1/2 mv squared. The mass of the block is 0.25 kilograms. So now we got to solve for V. Half of 0.25. That's 0.125. So we have 52.5 equal to 0.125 times V squared. So let's divide both sides by 0.125. So you should get 420 is equal to V squared. Now, let's take the square root of both sides, and this will give us a V. The square root of 420 is approximately 20.49, but we can round that and say that's about 20.5 meters per second. So this is how fast the block is going to move when it's released by the spring.